Wow!
This is for our math.
How's math class? It's great. Keep working. Gotta find the ambiguous case, the 30, 60, 90. Very important aspect. How are you, brother? Is that the work? You use math in that?
No.
Have to use math. Everything. Today, I will be teaching one of my favorite concepts in math. I will be proving the relationships between sides in a 30, 60, 90 triangle and a 45, 45, 90 triangle, respectively. So I can prove this even without using trig. Let's start with a 30, 60, 90. For this, let's begin with an equilateral triangle. Recall that an equilateral triangle has all angles equal to 60 degrees and all sides congruent. I'm going to set the sides equal to 2. It will be useful. To build our 30, 60, 90 triangle, we're going to drop an altitude from the top vertex. We know this will work to make our triangle because an altitude creates a 90-degree angle. We have a 60, so adding a 90 should complete our triangle. Once we drop the altitude, we learn a couple things. 1. Since degrees in a triangle add up to 180, we know that the top angle has to be 30. And 2. Since in an equilateral triangle, the altitude and the median are the same line, the base will be split perfectly in half. So I'm just going to draw a base there and split that in half, and that's going to be 1. As you can see, we know everything about this triangle except for the value of the altitude. To find it, let's use the fan favorite Pythagorean theorem. So, as we all know, the Pythagorean theorem is, at the basic level, c squared equals b squared plus a squared. We know c equals 2 and a equals 1, and let's write h for b. So, 2 squared equals h squared plus 1 squared. Now we can simplify. 4 squared equals h squared plus 1. And let's simplify it even further. 3 equals h squared. And finally, for the answer, h equals root 3. So after a little algebra, we end up with h equal to square root of 3. Let's look at a value table that might help clarify what we have learned. So I'm just going to draw a little value table, and it's going to really help us. So for a value table, let's start with 30, 60, and 90. So under each one, let's write 1 for 30, root 3 for 60, and 2 for 90. This is just for one specific triangle, but these ratios will hold for any 30, 60, 90. So next, we can put x under 30, x root 3 under 60, and 2x under 90, and proceed with x over 2, x root 3 over 2, and x. Next, we can go x root 3 over 3, x, and 2x root 3 over 3. These are all ratios to one another. You can plug in any number for x and quickly find the values of the other two sides. The reason I've written 3 versions of the equation here is so x can equal any one of the sides. For example, you're given a triangle where you know the hypotenuse is 7 and the angles are 30, 60, 90. You would use the second listed equation and set x equal to 7. Now let's start with the 45, 45, 90. Let's begin with a square. We know that a square has all angles equal to 90 and all sides congruent. Let's set sides equal to 1. I also drew a diagonal, and it will come into play later. So we label all 1, and we know that all angles are 90. The reason this is a 45, 45, 90 triangle is because we can see it's an isosceles triangle. Isosceles means that two sides are equal and two angles are equal. The two sides come from the square, but the two angles let us know that our other two are 45 and 45. So let's go ahead and label 45 and 45. So, just like last time, the only thing we are missing is one side, our hypotenuse. Let's label it H or C, or whatever you're really comfortable with. So, once again, it's Pythagorean o'clock. So let's do it. What do we have? Let's begin with the basic. C squared equals A squared plus B squared. Next, after I finish myself there. So next we can go to C squared equals 1 squared plus 1 squared, because that's what we do have. So next we simplify even more. C squared equals 1 plus 1. Next we go C squared equals 2. So after a little bit of algebra, we get that. And the final answer would be C root 2. And that's the same thing we did last time, and it makes it pretty easy for us. So now, let's make another table on the other side. This will definitely help us. So once again, we go 45, 45, and 90. So under the first 45, we can put 1, 1, and then root 2. For the next row, x, x, and x root 2. And finally, x root 2 over 2, x root 2 over 2, and then x for the 90. So, like the other table, depending on what you're given first, you can easily use the ratios, and you can find the other sides really, really easily. Before we move to the unit circle, there is one aspect of understanding a right triangle that must be learned. This is proving why sine of 30, 60, and 45 equal what they are, and why cosine of 30, 60, and 45 equal what they are. Starting with 30, 60, sine 60 equals cosine of 30. That's just the base. Cosine of angle 30 is adjacent side, being x root 3, and the hypotenuse being 2x. When we cancel out the x's, it becomes root 3 over 2. Right here. That's all we're talking about. It's very easy stuff. So, for the cosine of 30, it's just like here, and so it's adjacent over hypotenuse, you cancel out the x's, root 3 over 2. The interesting thing is that the sine of 60 being opposite over hypotenuse is the same exact thing, making them equal to each other. The other equation states that cosine 60 equals sine of 30, right down here. The opposite side of 30 is x, and the hypotenuse is 2x. And when cancelled out, this equals 1/2. Like the other ones, when you look from the top angle of 60, it is apparent that cosine of 60 is the same ratio. This will justify the values of any right triangle containing angles of 30 and 60 in our unit circle. Now, for a 45, 45, 90, it's a little simpler, but it is actually the same concept. Sine of 45 equals cosine of 45, and that would equal x over x root 2. When the x's are cancelled out, it becomes 1 over root 2. And finally, it can be switched around to root 2 over 2. Since they are the same value, it is important to note that cosine and sine are justified throughout the unit table for a 45, 45, 90 triangle throughout. Just like we see here, both sines and both cosines are going to be equal. The unit circle is an important and helpful tool in geometry and trig, and how it relates to the charts that I made for you guys is actually very relevant. For a unit circle, let's start with a circle and a coordinate plane. To begin, we want to label a 30 and a 45 and a 60-degree angle. We also want to reflect them in each quadrant. In the second, it would be 120, 135, 150, and then finally to 180. The third quadrant would be 210, 225, 240, and then finally 270. Lastly, in the fourth quadrant, it would be 300, 315, 330, and then finally 360. Something to remember is that when you make your unit circle, put another angle that is reflective across all four quadrants. If we start with a 30-degree angle, for example, we know from our charts and knowledge about sine and cosine of 60 and 30 that those coordinates will be root 3 over 2. for x and 1 over 2 for sine. This point would be root 3 over 2 as x and then 1 over 2 as y. X will always be cosine and y will always be sine, as angle theta, or 30 in this case, tells us so. Something to know is that each segment on the circle is 1. So we know that the lengths of that side, and from what we've learned in our charts and videos explaining why sine is sine and cosine is cosine, we can easily fill in those points. Once we know what our coordinates are, we have to identify what quadrant this angle would fit in. Something that might help you when you get a negative and a negative or positive and negative coordinates is the phrase, all students take calc. In the first quadrant, A for all points are positive. In the second, only sine is positive, and in the third, tangent is positive, meaning cosine and sine are negative. In the fourth, only cosine is positive. From now on, we can use logic to form our next points. From 45 to 60 all the way to 330, we will easily identify what quadrant and what angle we are talking about. We also know everything about our angles that we need to be comfortable and to master our trig knowledge.
Okay.
Do you like math?
Not really.
Oh, God, love math! Grasp the universe.